A very good afternoon to you. We're going to begin the post-lunch session and hope that the delicious food hasn't got to you. So please stay awake because we have a very exciting speaker, Professor Sudipta Dash from Vishwa Bharati. And she's going to talk about remembering AKR, right? Sudipta has worked extensively on cosmology. She has been a student of her advisor, who is a direct AKR student, Professor Narayan Banerjee, whom we have seen. So Sudipta, all yours.
First of all, I would like to thank the organizers for inviting me to deliver a lecture in this AKR Centenary program. So before I go to the technical part of my talk, first I will just share some of my thoughts about AKR. I was not a direct student of AKR, but the Relativity and Cosmology Research Center at Jadavpur University, from where I did my PhD, we used to have a weekly seminar on every Tuesday, and AKR used to visit the center every Tuesday. And there actually I first saw AKR, and at that time I was just a beginning PhD student, so I never had much of academic interaction with AKR, but what I have seen is he was a very caring person. He was very fond of his students. And this picture, I think it was taken during a seminar lecture. It was held in some 2004, as far as I remember. AKR passed away in 2005, and he wrote his last paper in the year, his last paper was published in the year 2004. And this seminar lecture, when he was giving, it was when he was 81 years old. So, and NB can correct me, I think this was the last lecture he gave in Jadavpur University or in the center. And there he actually discussed about what he has worked on in his last paper. My personal interaction with AKR was every Tuesday we had the ritual, not ritual, means we used to go to AKR's house to bring him to the department. So, yeah, that was towards the end. So usually means what I have seen after I joined. So usually Professor Narayan Banerjee used to go and bring AKR. So one Tuesday NB was busy for some reason, and so I volunteered to go to his house. And I was very excited that I will go to bring AKR. So when I reached AKR's house and he first saw me, I was very thin at that time. So he started laughing. He said, "They have sent you to bring me." So let's do one thing. Today I will take you to the department. I will go, you come with me, I will take you to the department. The idea was I am stronger. At the age of 81 also I am stronger than you. So he was very, very friendly with the students. NB again means suppose we are discussing about the teachers who have taught us, and usually we used to have a debate. We used to argue that we have been taught by very good teachers, and NB, he has a very quoted dialogue. He used to say that you may be taught by good teachers, but you will never be able to claim that you have been taught by star teachers like AKR, S.N. Ghoshal, and etc. So maybe I agree with him that we may not be taught by star teacher like AKR, but means we may not have received primary radiation from this star teacher, but the secondary radiation that we have received through his students, that was good enough to enlighten our mind. And what I think is AKR was obviously he's a great scientist, and that's why we are celebrating his centenary year. But AKR also is a very good teacher. Means he could impart the passion for physics in his students for generations of batches, and his students are basically carrying on the legacy, and they are basically inspiring the next generation of students, and they are inspiring them to, they are teaching them how to take physics as a passion. So one thing I would just like to mention, when I started my research as a in cosmology. This is the very first book which I came across, the theoretical cosmology book by AKR. Later on, he wrote another book on GTR and astrophysics and cosmology with Professor Sriranjan Banerjee and Professor Rashid Banerjee. But this book, the theoretical cosmology book, Professor Parangama Sen, AKR's daughter, she was once saying that this book was very close to AKR's heart. And even now, when I teach my students some basics of this FRW theory or the cosmic distance ladder or the magnitude redshift relationship, etc., I always ask them to go through this book. And this can be the basic, means to start or to begin with the basic understanding of cosmology. This can be a very good book for any student who is going to pursue research in cosmology. So with these few words, I would now go to the technical part of my talk. So title of my talk is to test models beyond ΛCDM. So the outline of the talk is as follows. Means first I will talk. I will give a very brief overview about the standard cosmological model, and I will put emphasis on why should one has to look beyond the ΛCDM model, and then I will talk about one or two models beyond this ΛCDM model and how to constrain these models using different methods. So as we know that the universe is accelerating at present, and two separate groups, the Supernova Cosmology Project Group and the HiZ Supernova Search Team, they have independently observed this accelerated expansion, and the 2011 Nobel Prize was also conferred to them for the discovery of this accelerated expansion of the universe. And as we know that around 95% of the energy density of the universe is unknown to us in the form of dark matter or dark energy, and we know only the 5% of the universe is known to us in terms of visible matter in any wavelength. So if the universe is expanding with an acceleration, what is the reason behind it? So the physicists, they consider there are mainly two approaches. So either there is something wrong with the gravity and one can modify the gravity sector, or one can consider that there is some unknown exotic component which is providing some anti-gravity effect, so that the universe, instead of decelerating, it has started accelerating, and we popularly call it a dark energy. Or apart from this, there may be a completely new physics which is unknown to us. So what do we want, or what do we need from a standard cosmological model? So if we start with standard Big Bang, then that will be followed by inflation. Then we have this recombination era. We have this reionization era where the first stars were formed. After that, there will be galaxy formation, and then we have this present accelerated expansion in terms of dark energy. And obviously, at different time scales, we have different types of observations in support of this. For example, for 21 centimeter experiments will study the reionization history. For dark energy, we have this type 1 supernova observations, lensing observations, and etc. So in a gist, what do we have in a standard model? We have this inflationary era followed by radiation dominated era, then a matter dominated era, and finally one has to explain this late time acceleration. And the ΛCDM model, or the cosmological constant model, it happens to be one of the simplest models who can explain this phenomena very well. And if we consider the expansion rate of the universe in terms of ΛCDM, then this omega m factor, it takes part of the cold dark matter component, that 23% plus 5%. We have this omega lambda component, which is the component due to this ΛCDM cosmology, and one can consider radiation in radiation component as well, but this component being small, we often neglect it. But so what are the advantages of this ΛCDM model? It has been found that this ΛCDM model, it more or less it fits with data pretty well, and most of the observations like the CMB, BA, or the supernova observations, the ΛCDM model fits very well with them. But there is a problem with this cosmological constant, or the ΛCDM model, and we call it the cosmological constant problem. The value which is assigned by the cosmology from the cosmological context, and the value which is assigned from the quantum field theory or from the high energy physics context, these two values have some 10 to the power 120 order of magnitude difference between these two. But apart from this, recently the ΛCDM model has been exposed to two more problems. One is the Hubble tension and another is the sigmoid tension or S8 tension. So for Hubble tension, what it says that if we consider the Planck data, especially the Planck 2015 or Planck 2018 data along with the BOA data, they predict the value of H0 to be somewhat around 67, 68. Whereas if we consider the measurements from the shoes data or from the holy cow data, they measure the value of the Hubble parameter, current value of the Hubble parameter on the higher side around 75, 74, 75 and etc. So there is a huge discrepancy between these two. And this Planck data, they actually consider ΛCDM model as the base model, whereas this shoes data, these are basically model independent. They do the measurements in a model independent way. So they mainly make the measurements from the gravitational lensing and other ways. So there is a discrepancy in the value measured from the early data. CMB data is obviously it corresponds to the early universe. So there is a discrepancy in the value of measurements from early universe and the late time data. So this tensions, and we say that the value of H0 is in tension, and if one looks at these values, the value obtained from the Planck 2018 data and the shoes data, there is a 5 sigma difference between the values of obtained by these two different methods. Apart from this Hubble tension, there is another tension which is known as the sigmoid tension, and ΛCDM model actually suffers from this sigmoid tension as well. One can see that if we look from if we consider the Planck data and the DES data, then the value of omega m, the predicted value of omega m is lesser than 0.3, or the value of sigma 8, it is around 0.8 or higher. But if we look at the KIRS data or the BOS data, then the value of omega m, it comes out to be higher than 0.3, and similarly the value of sigma 8 is lesser than 0.7, and accordingly, since S8 is related to these two, accordingly there is a tension in the value of S8 as well. So again, the predicted value of S8 and predicted value of S8 from these two measurements, they are also in tension, and this tells us that one has to look beyond a ΛCDM model. So because since there is a discrepancy in these two data sets, so the very first question one arises in one's mind is there any problem with the data set? Is there any problem in the systematics? But both these groups, they have, means the groups, they consider that there is no systematic error. Then obviously the question that comes in our mind is then, is it in the model? If does one has to look beyond the ΛCDM model? So
the slide again, the constraints.
Sorry. This one?
Yeah, can you just put that? Okay. Now, is the conflict in the context of SA2 conflict between Planck, which is CMB, versus local large-scale structure? That's very much like what is happening with the extra tension.
Same thing.
So it's
local versus CMB. Yeah. Because these data sets are basically from the weak lensing. Can I? Yes. So one has to look beyond a ΛCDM model. So the situation of cosmologists is like this fairy tale prince who is looking for Cinderella so that the shoes data actually matches. So what are the possibilities if one wants to look beyond the ΛCDM model? What are the possible alternatives? Again, there are two approaches. One can either modify the geometry sector, or one can modify the matter sector, as I have described earlier. So if I modify the geometry sector, then the modified gravity models actually fall under this category. And if we modify the matter sector, the most popular candidate is a dynamical dark energy model. So in this talk, I will be putting emphasis on this dynamical dark energy model, and I will be mainly talking about some parameterized dark energy model, and in this context, I will talk about phantom scalar field model and little bit about the interacting dark energy models. But there are a number of other models also available in literature.
Is there any single observation that can help us distinguish those?
Not really, means observationally one can't say, because the approach is completely different, because in modified gravity model you are modifying the Einstein-Hilbert action. So the field equations, it's,
This growth factor, etc.
yeah, means no, actually both these sectors means if you consider the modified gravity models or you consider the modified matter sector, in both of them if you constrain or if you confront with the observational data, somehow both of them have some means matching with they match with the observation in some or some limit. So it's not that observationally one can distinguish between these two types of models, means as far as I know. So before I proceed, there are just a few open issues which a cosmologist would like to answer. First of all, as I told you that dark energy, it has to produce an anti-gravity effect, and till now we don't know of any component which can produce an anti-gravity effect. So what can be the nature of dark energy? This is an open question, and can it be dynamical? Is it ΛCDM or it's a dynamical dark energy? Number two, if the current universe is accelerating, will the acceleration go on forever or will the acceleration slow down? So this is another open question which the cosmologists want to answer. Will the cosmic acceleration speed up in future? Is the late time acceleration and the early time acceleration, the inflation, are they somehow connected? Can you have a single field or a single model which can explain both these early time acceleration as well as the late time acceleration? Another open issue is if we consider a modified gravity model, it has to, first of all, it has to address all these issues, and apart from that, it should give us GR, the general theory of relativity, back in some limit, because general theory of relativity, it has this number of observational evidences in its favor, like the perihelion shift of Mercury or the gravitational lensing. So if we modify the gravity sector, then it should explain, either it has to explain this phenomena or it has to give us GR back in some limit. And also this Hubble tension and sigma 8 tension, what Sriram was trying to ask, are they related or they are completely uncorrelated? So this is another open issue that people want to address. Yeah.
There are various ways when people are trying to understand the origin of the dark energy, from some fundamental principle. But for dynamical dark energy, after some effort that from some fundamental principle, you can argue that why the dark energy will be
actually, means what I consider is, means my answer to your question will be, means there is no reason to consider that it is not a dynamical, means or rather I would say, means since ΛCDM model, I know that it's a very good, it's very well fitted model, but since it has got some problems, for example the cosmic coincidence problem, why the dark energy becomes dominated at late times. So if we consider a dynamical nature of this dark energy, then these problems can be elevated.
Suppose fundamental supergravity model or string model where some possible origin of this dark energy because of some symmetry breaking, etc. There are a lot of problems. So in all those cases they are constants, but here you are trying to make it dynamical. So
yeah, people have worked with Higgs scalar fields also. Means Higgs scalar fields can.
But there is no answer, so some kind of moduli fields, is something like that. Okay.
Yeah. Okay. Okay, so if we modify, I will just spend one slide on this modifying gravity sector because I will not go into the details of this. So in the modified gravity sector, we have this FR gravity, the Gauss-Bonnet gravity, the teleparallel gravity, the Brans-Dicke theory, and so on. So in all these theories, what happens is the Einstein-Hilbert action is modified using some particular functional form, and depending on that, the modifications are done. But there are some issues with the FR gravity models. For example, the for obtaining current accelerated expansion, one needs inverse powers of R, whereas for early inflationary universe, one needs positive powers of R. And R inverse models, they have some issues regarding the stability. But again, it has been shown that with R inverse, if one adds a positive power of R, then these instabilities disappear. So usually people consider different polynomial powers for this FR gravity models or others, but there are various functional forms, but I will not go into these details. So So I will be putting emphasis on this dynamical dark energy models, where the as a candidate for dynamical dark energy model, the scalar field models, they serve as the best candidate or one of the most popular candidates as dynamical dark energy model. So for scalar field models, the Lagrangian for the scalar field is given like this, where you have the kinetic part and the potential part, and from this Lagrangian one can obtain the scalar field energy density and the pressure component for the scalar field in this form. This is very standard expressions. So with this, the Einstein field equations and the Klein-Gordon equation, they can be written in this format. So the Hubble parameter or the expansion factor, now it has got this omega m, and apart from this we have now this dynamical scalar field which is now evolving as compared to a ΛCDM model. So what are the cosmological parameters that cosmologists are interested in? First of all, the rate of expansion, the Hubble parameter, the deceleration parameter q, which gives us the rate of acceleration, and the equation of state parameter, which will provide us information regarding the dynamics of the scalar field. So the usual approach is to consider a potential for the scalar field, because it is dynamical, because if you have a potential, the scalar field will roll down the potential and one can eventually find out the dynamics. So usual approach is to consider a potential for the scalar field, and from that one can study the dynamics of determine the different cosmological parameters and study the dynamics. But in most of the cases it has been found that the potential which one is when considered to get the correct rate of expansion or to get the correct structure formation of the universe, one has to fine tune the parameters of the potential to a large extent. So these models are usually very highly fine tuned. So what can be an alternative approach? An alternative approach is if one considers a functional form for this Hubble parameter or the deceleration parameter or the equation of state parameter, and one can construct the dark energy model from that, and one can confront this with the observational data, and this is what is done in a parameterized dark energy model. So in parameterized dark energy model, people usually consider a functional form for any of these cosmological parameters, and they confront this model with the observational data. They find out the values of these parameters from observational data, and then they study the dynamics of the scalar field. So I have listed down few examples of this parameterized dark energy model. So in this slide I have listed the examples where people have considered different parametric forms for the equation of state parameters. So it may be linear parameterization, it may be a CPL parameterization of this form, JBP parameterization, which is basically a modification of this CPL one. One can consider a polynomial parameterization, one can consider a W0 flat, means this Brout et al, they call it flat W0 ΛCDM model, and etc. But and in fact there are many other functional forms for W has been chosen by different authors. But the concern is whether these parameterized dark energy models can solve the Hubble tension or not. So if we consider this last example from this paper, so it has been found that if we consider the Pantheon and the Shoes data together, the value of H0, it comes out to be around 73.3 for this flat W0 ΛCDM model. Whereas if we consider the Planck data, then the value it comes down to 67.4. So the tension remains, means this, and in fact this is the case for most of these parameterized W5 models, where the parameterization of the W5, the parameterized W5 models, they are not found to be very effective in solving the Hubble tension or the sigma tension. What happens if we consider a parameter?
Do they include perturbations in dark energy?
People have worked on perturbations of dark energies as well. Means there are many papers who have worked on. In fact, I myself, we have considered these perturbations of these dark energy models as well.
Does that change anything?
Not much. I will come to one example. Not much. So if we consider instead of parameterizing W, if we parameterize Q, then what happens? There are again a number of examples. So again, one can consider a linear parameterization, one can consider a parameterization like CPL parameterization, one can consider a polynomial parameterization, and so on. So what is the result? So if you consider linear parameterization or a CPL type of parameterization or a polynomial parameterization, in all these cases you can see the value of H0 is around 69, 70 or like that. That means one can say that the Hubble tension means the tension has reduced little bit, but it's not that the tension has been solved, means it cannot reach the value as high as 74. So one can also consider a parameterized H model, H of Z model, where different parameterized form of Hubble parameter has also been considered, where one can consider a polynomial for a Hubble parameter, or one can also consider a time dependence for the Hubble parameter. For all these cases also it has been found that the Hubble tension means or the sigmoid tension hasn't been solved completely. For example, for this first one, if you consider the this polynomial potential, or if you consider this potential, one can see that the value of Hubble parameter, it comes out to be around 68. We have used the Pantheon, BO and SDSS data. The value of H0 it comes out to be around 68.7. Here in this paper you can see that if we consider only the cosmic chronometer and the BOA data, the value of Hubble parameter is around 68, but as soon as we include the Pantheon data, the value shifts to 74. So the tension and the Hubble tension, it remains, means one could not solve the Hubble tension using this parameterized dark energy models. Then what is the?
Why did you expect they may improve the Hubble tension in the first place?
People are just.
What guided you to construct those edge of Z?
No, actually it was just a, one can say that a trial and error method, that whether it solves the Hubble tension or not. Actually by this trial and error method people has succeeded. I am coming to that. So as I was saying that there is a ray of hope if one considers a phantom scalar field model. For phantom scalar field model, it has been means the equation of state is basically less than -1, and if one considers the equation of state parameter less than -1, it has been, say here you can see that this has been this paper is by Valentino et al. That if you they have considered a one parameter dark energy model where the equation of state parameter they have considered constraint to be value which is less than -1, and they have found that the value of H0 is around 72 and 74 for different data sets. So, but again, means if we consider the Planck data, it has been found that this Valentino et al. They have found that if you consider Planck data, then the Planck data prefers a quintessence equation of state, where the equation of state is greater than -1. But if we consider the BOA data and the Pantheon data prefers a value which is less than -1, but greater than -1. But for the BOA data, it prefers a phantom scalar field or phantom model where the W is less than basically -1. So people have actually studied a number of phantom dark energy models. So the Young et al. They have studied a number of one parameter dynamical dark energy models where they have considered a single parameter W0. And what they did is they considered different values of W0 to start with. They considered for one set they considered the value of W0 to be around -0.9, which is in the quintessence region, and for the other set they considered the value of W0 to be on the phantom side, which is greater than less than -1, -1.2. But in both these cases, what they found that the trend for this Wx or the equation of state parameter, it always shows a decreasing trend with evolution. So whether it is phantom or whether it is quintessence, the parameter W will always have a decreasing trend, and there is a chance that even though we start with a quintessence field, in future it may evolve to a phantom scalar field, phantom model. And if we look at the corresponding values of this H0 for these different models, for each of them you can see from the CMB data or from the BO data, the value of H0 has increased, and it can be as high as 84. We don't need that much high value, but means to start with one can actually means one can get a higher value of H0. Now one can consider a suitable parameterized form of this phantom model to get a lower value of H0 and so on. So what the gist is that all this data set they prefer a phantom dark energy equation of state, at least today. But the problem is okay.
All have considerable error bars. You say
Yeah.
it's phantom,
Yeah.
but the error bars are as much as 1.
I agree. So What is but there is a issue with this phantom scalar field models as well. So the dynamics of phantom scalar field model in the kinetic energy part, the kinetic energy part itself is negative for a phantom scalar field model, and accordingly this 1 plus W phi it is less than 0. So the kinetic part will be negative, but rho phi itself is positive because energy density we do not consider it to be negative. So what happens in a phantom-like equation of state is that it effectively speeds up the acceleration of the universe, which will result in a higher value of H0. But the problem is, if the universe always remains phantom, then the structures of the universe will not be formed. We will not see the universe as we see it today. So obviously the universe cannot be phantom always. It cannot, the equation of state cannot be phantom always. So one needs a phantom crossing in dark energy evolution. Otherwise the structures will not be formed. So we propose a general prescription to study this quintessence as well as the phantom models at one go. So what we do is we introduce a parameter epsilon, we name it as switch parameter, and this parameter epsilon, if it is positive, it will describe a quintessence scalar field, and if it is -1, then it will describe a phantom scalar field. And all the equations can be recast or can be rewritten in terms of including this switch parameter. So all the model parameters, means the potential of the scalar field, the Hubble parameter, and all these parameters one can write in terms of this dimensionless, the normalized Hubble parameter E, which is basically h of z by h0. So one can recast all these cosmological parameters in terms of this normalized Hubble parameter. So if one has a parameterized form for this normalized Hubble parameter, one can actually find out the condition that when this phantom barrier crossing will take place, because this W phi also one can express it in this form. And when we are obtaining this expression for W phi, there is no assumption regarding the model. It's just from the field equations. Sorry? Yep. No, it's the evolution of the W phi. W phi will evolve and
Considering one or the other.
epsilon, we have kept it as epsilon. We don't pick up any value.
People are misunderstanding it as it's dynamic or changing with time. It's not.
It's not flipping from plus to minus, something like that.
It is. It is.
That is what I thought.
It is because we have this. Let me go to the previous slide. We have this phi dot, and in the d phi dz we have this epsilon sitting. No, epsilon is constant, but the epsilon will be sitting inside phi dot. So phi dot is being dynamical, d phi dt, that being, or d phi dz, that being dynamical, that will actually in turn will change W phi.
You are either considering a phantom model or not phantom model.
Yeah, but you can study both of them using the same set of field equations.
That is fine.
No, but I'm claiming that with time, at some point of time, it will flip side.
I will come to it. Okay, so sorry. So if you look at this expression for W phi, if it is this d dz and we have this quantity inside the bracket, if this quantity inside the bracket is positive, we will have a quintessence model. If the quantity inside this bracket is less than 0, then we will have a phantom model. And one can actually find a general condition for this phantom barrier crossing. If when this quantity becomes 0, at that time the equation of state parameter will transit from non-phantom to phantom era, and one can actually find out at what redshift this transition from non-phantom to.
It's confusing actually. Okay, so look, it cannot. You start. What is your source of dark energy? The field, scalar field, right? You have to start with epsilon equal to 1 or -1. That's it.
Okay, even if we start with epsilon is equal to +1, means the dynamics of the scalar field can be such that one can, the W phi, it can cross the -1 line and it can go to the non-phantom era. But means it's not that we are.
W is different. W is different. We are not talking about W.
Okay, can I discuss it later after my talk? Yeah. So let us take a toy model to explain what I mean. So suppose we consider this parametric form for this h of z. So w phi one can obtain in this form, where this w0, w1, w3, they are basically in terms of this model parameters. So one can recast this equation in this form, minus 1 plus some delta, where delta will be a function of w0, w1, w2 and w3. So depending upon these values w0, w1, w2, one can it can either be phantom or it can be a
So if you are suggesting that h of z, and for those h of z, you can have a phantom crossing. That's what you're saying.
yes. So we have confronted this with this following set of data, and what we have found that the value of H0, it comes out to be around 68.9, and W dark energy is just slightly phantom, it's minus 1.4. So you can see that this model, it could not solve the Hubble tension to a, although the equation of the state parameter is phantom in nature, but it could not solve the Hubble tension to it could not solve the Hubble tension. So apart from this
Say equation of state is phantom. That is just minus 1, right?
less than minus 1 is phantom.
Or less than that would be.
Any value less than minus 1 is phantom. So we considered another example, means this is from this paper. So this W dark energy, it's a phantom crossing model. That means because we have this evolution in this A. So when with the evolution in A, one can actually cross from a phantom to a non-phantom to a phantom era. So here also you can see that these blue ones, they correspond to the Schurz data, means LSS plus Schurz data, whereas the red ones, they correspond to the supernova data. And one can see that for the blue line, the transition has taken place, the phantom transition, the transition to the non-phantom era, it has taken place earlier, and the value is much more phantom, it's around minus 2, whereas for the red line the value is slightly phantom, which is less than slightly less than minus 1, and you can see the difference in the values. For the blue line the value is as high as 74, whereas for the red line, for the red one, the value is around 68. So apart from the transition redshift, the value, how much phantom it is, it's not that if the value is just close to minus 1 it will be able to solve the Hubble tension. It has to be much lesser than minus 1, and in that case only it can solve the Hubble tension. This is what has been shown. So what this generic analytic approach, it actually showed that one can solve the Hubble if one needs to solve the Hubble tension, then this requires this W dark energy to cross the value minus 1. From non-phantom it should cross to the phantom era, and for simultaneously if one wants to solve the Hubble tension and the sigma tension, this WZ, it must cross the phantom limit, and this has been shown by many authors.
At some Z or the same Z?
No, at different Z, at different Z. This will depend upon the parametric model where the phantom crossing will take place. The earlier the phantom crossing takes place, the more likely it is to solve the Hubble tension, because the more phantom it will be in nature. So another aspect is, can these interacting models, interacting dark energy, dark matter model help in solving the Hubble tension? So why should one consider an interacting dark energy dark matter model? Because since nothing is known about the dark energy or the dark matter component, an interaction between them may provide a more general scenario. And as I was mentioning that if you consider an interacting model, then this can elevate the coincidence problem also, and it can provide an answer to why the dark energy becomes dominant at later times. So if you consider an interaction between these two models, the conservation equation, it will get modified, and we have a source term now sitting on the right hand side. Now regarding what people do is, people usually choose the form of Q phenomenologically, and the popular choices of Q are either it is proportional to H times the cold dark matter, or H times the raw dark matter, or a combination of these two. Now why this particular form? The answer is basically because these are very simple, and also they are dimensionally correct, because for this equation to be dimensionally correct, we need a inverse power of time and a quantity which has the dimension same as the equation of state parameter, and then this h times rho dark energy and h times rho c, they are the very popular choices. But people have tried to obtain this interaction starting from the first principle, starting from the action itself, but there has not been much of a success where people can obtain this interaction directly from the Lagrangian. So usually the choice is made phenomenologically. So let us see whether these interacting models can solve the Hubble tension or not. Again, in this paper, Valentino et al., they have considered a form of Q which is proportional to h times rho dark energy, and they found that if we consider for this interaction, this H0 value, it comes out to be around 74, both for Planck and this is Pantheon data along with some Gaussian prior, so they call it R19. So for both these data sets, for weak lensing data as well as for the Pantheon data, they obtain a higher value of H naught if one considers an interaction between these dark matter and dark energy candidates. This is another example where they have considered some arbitrary form of this interaction, and here also they have shown that for different data sets there is the Hubble tension, it has been reduced, and one can get a higher value of the Hubble tension or the sigmoid value if one considers an interaction between these two components. So what about a parameterized interacting dark energy model? If we consider in this paper, again the form of Q has been chosen to be some beta times h rho dark energy, and we consider a parametric form of W dark energy. This actually follows from if one considers a double exponential potential, then one arrives at this type of equation of state parameter. So we have studied this for 3 different cases regarding the strength of interaction. We have considered the strength of interaction to be from higher value to much smaller value. And what has been observed is that if we consider this for higher value of strength of interaction, this although in the matter density contrast there is not much of an impact, but in the if one looks at the perturbation and study the dark energy density contrast, then if the rate of interaction is higher, this will have significant impact on this will leave significant imprints on the density contrast for the dark energy as well as for dark matter, because the density contrast will now also be there will be imprints on the density contrast as well if one considers a very high value for this interaction rate. And if one confronts this model with these observations, again the value of H0, one obtains the value of H0 to be around 70 or so. So we cannot say that the Hubble tension has been resolved, but it has been elevated, and maybe this has been just an example, a toy model. So one can consider some other parametric form of W and can check whether the Hubble tension can be resolved for this interacting dark energy and dark matter models. So what are the tools a cosmologist, do I have 2-3 more minutes? Yeah, okay, thank you. So what are the tools that a cosmologist use? The first tool is using this MCMC analysis. So we have observational data, we fit into it, we have a cosmological model, we perform the chi-square analysis, and we confront the model with observation and put constraints on this model parameters. Another method is to use the cosmographic parameters, which puts geometrical constraints on different model parameters. And then we have this dynamical system analysis, which helps to understand the behavior of the system mathematically. I will not go into this, so I'll just spend last 2 minutes of my talk on this cosmographic parameters, how these cosmographic parameters are used to differentiate among different dark energy models. So the cosmographic parameters which cosmologists generally use are the deceleration parameter I have already described, the jerk parameter, which is basically the derivative of this deceleration parameter. So it will give us the rate of acceleration, and this will basically tell us whether the acceleration will slow down or whether it will speed up in future. Then we have this snap parameter, but instead of snap parameter, people usually study the combination of these 2 parameters, the state finder pair and the Ohm diagnostic. So I'll just go through them one by one very quickly. So for deceleration parameter, as I told that the universe, if it accelerates forever, then our structures can never be formed. So what we need is that there should be a flip in the deceleration parameter, so that earlier at earlier time the universe was decelerating, so that the structures, the matter can come together and structures are formed, and at late time it becomes accelerating. So any model, if it doesn't have this signature flip, that can be actually that doesn't match the cosmological scenario completely. So this is one cosmographic parameter people usually check. The second one is this jerk parameter. So this basically helps us to differentiate among these different dark energy models, and it actually helps us to measure the deviation from the lambda CDM model. This j is equal to 1 value, it corresponds to the lambda CDM model. So if the more it deviates from the lambda CDM model, one can actually check that whether it is providing acceleration or deceleration. Here a decreasing slope or a negative slope will basically represent a decelerating expansion, whereas a positive slope will represent an accelerated expansion. And for this example, for example, one can say for this parameterization, one can show that this deceleration parameter, the jerk parameter, in future z less than 0, in future it again accelerates, and then it will basically again decelerate, and so the rate of, for this particular model, the rate of deceleration means the universe will be decelerating again in near future. If we consider the state finder pairs, here it actually basically helps us to discriminate between different dark energy models. So if r is equal to 1 and s is equal to 0, this point it will correspond to a lambda CDM model, and one can from this one can actually check whether how much our model has how much it is different from the lambda CDM model. So this range means this region, the r less than 1 and s greater than 0, this corresponds to the quintessence model. This part it corresponds to the Chaplygin gas model, and here for this particular example, one can see that there is in the SR plane the trajectory it actually swirls back. This means that lambda CDM model is an attractor. So whatever model we are considering, ultimately with evolution it will basically go to the lambda CDM model. So this is less likely to solve the Hubble tension. Yeah, and this is the last slide. So for the Ohm diagnostics again, if a negative slope will correspond to quintessence model and a positive slope will correspond to a phantom field, and the more phantom it is, more likely it is to solve the Hubble tension. So where do we stand? We have this discrepancy regarding the measurement of Hubble parameter corresponding to early data, early time observation and late time observation, and people are trying to put together and come to a solution to solve this Hubble tension, but till now there has not been much of success. There has been few, but there has not been much of success. So people, maybe future data will help us to means we need more data to solve this Hubble tension. So with this, I will thank you.
Thank you very much for a wonderful talk. We have some time for questions. There. Sudipta.
Yes.
But you can answer from there. Yeah. Okay, fine.
Okay.
Thank you, madam. It's very informative and nice talk.
Thank you.
So I have several questions. Can I do one by one? So my first question is
We
non-technical.
ask two questions because there are others, and then we can come back to you.
Okay, only two questions.
I can talk to you regarding different
So
detail.
just think about it in future. We got some kind of modified gravity theories that explains all well are connecting the early and late and solves the dynamical dark energy or cosmological coincidence problem and the constant problem. So in modified gravity theory, which dark energy we get, that is completely geometrical dark energy, right? So if they are a function of R or in the Q, so then can we can say that on that time that dark energy source is full geometrical or a gravitational anti-gravity effect. So how can we say that in generally we keep the dark energy component, it's clubbing matter section. So it is not a it is not a fluctuation of that dark energy is completely geometrical.
Okay, can I answer this question first? Means when you are doing modified gravity models, you don't need dark energy. right? Because either you will modify the gravity sector, or either you will modify the geometry sector, or you will modify the matter sector. So if you are modifying the geometry sector, from there only if you can explain the current acceleration, why do you need an exotic component like dark energy? You don't need it anymore.
Thank you. And in last question, you have extend the parameter from single parameter dark energy model to omega 1, omega 2, omega 3, several parameters. So is it the right way if I increase more parameters, 6 to 7, so there is no bound, there should be a physical bound, or is it only fully phenomenological?
In fact, the maxima means 2 parameter models or 1 parameter models are the best to explore, because as we go on increasing the number of parameters, you are basically the means you have more what to say, means
Predictive.
yeah, means the predictivity actually increases. So the better way is to reduce the if you can obtain a dark energy model where you can explain all this with lesser number of parameters, that will be the best thing to do. But since people couldn't do that, so they go for higher parameter. But the best thing is either a 1 parameter or a 2 parameter model.
Thank you.
Thank you. Any other question? Over there.
Is the scalar field dark energy satisfied the energy condition?
Which energy condition? Because there are this dominant energy condition.
Weak energy condition, rho must be greater than or equal.
Yes, that's why we are always considering rho to be positive, so that it satisfies this energy condition.
Thank you.
Any other question or comment? Sriram?
Two related questions. What is the maximum change in chi-squared with these additional parameters that you obtain? Or equivalently, have you been able to calculate the Bayesian evidence? Is the change significant?
Yeah, we have mainly performed the chi-square analysis. We haven't considered the Bayesian evidence, but for chi-square also means the minimum value of chi-square is means if it's very high, then obviously this is not going to give us a very good corresponding to ΛCDM model.
What is the change from the ΛCDM model to the model that pushes your H0 value to 70?
I don't have the parameters now, because we usually check this AIC and BIC criteria. So the means there is a limit, means when we check this AIC and BIC, there is a limit, means if it's greater than that value, then one has to discard that model. So for our model, the value was within that limit. I don't have the values
You had
now.
another question? Just a second. Okay. Shomit.
Sudipta, there is a large volume of work. I mean, we have also done at one point of time that with scalar field theory with non-canonical kinetic term, right? And where you have the advantage of transition from a phantom to non-phantom. So do you think such models can help to explain this?
I have also worked on non-canonical scalar field dark energy, but at that time I didn't consider the non-phantom era, but maybe
if you consider that, right? So I was just wondering.
Yeah.
And secondly, your different kind of parameterization essentially was taking different kind of scalar potential. Am I right?
Actually, all these parameters are related. Means once I choose a W, basically the Q is also related.
I agree. But it corresponds to some background scalar field potentials are changing. And now for each of them, from the scalar tensor dual theory and FR kind of model, there exists a kind of corresponding FR theory. So has anybody kind of created these various models with what are the corresponding FR structure for this kind of model? Higher curvature gravity structure?
People have worked on it at that time, but I don't remember the exact.
Because that can be very interesting, that what kind of higher curvature gravity is giving rise to these kind of models. Right?
Yeah, for example, one of the examples I have showed, that corresponds to a double exponential potential.
Yeah, that's right. But so that can be, you can generate that from higher curvature gravity.
Because one can consider the Palatini formalism, and from the Palatini approach, one can actually reconstruct what can be the FR.
That's right, exactly.
But for all these models, this may not be true, because the form of potential means when you are considering some exotic expression for say Q or
it may
A.
not be invertible, right?
Yeah.
You are saying that, but
Yeah.
still, at least we know that there exists some. So you can prove some kind of existence.
Means often it happens that the value of V5 means the potential we cannot find out, so we numerically find out V5
That's
and
right,
we
exactly,
plot it. So
exactly.
that is not very exact. One cannot say that exactly it will
correspond to which
correspond
effort.
to
Okay. Okay.
Any other question or comment?
I have two clarifications. Okay, Professor Shankar is asking. So in principle, you can modify both the gravity sector and the matter sector. There is nothing wrong in it actually.
Yeah.
So I think somebody was saying that you were saying, right? So you can do that. But there is no reason to believe that you just want to modify one of them. So there are models where people have tried to address the dark matter problem. In fact, I remember one French guy who wrote a paper a couple of years back where they modified everything. So there are papers where people deal with modifications in the gravity sector as well as the matter sector. That's a comment.
Yeah, I had two clarifications, one for Sriram's question and one for Professor Soumitra Sengupta's question. Sriram asked what is the extent of the change in the chi-square. So now, usually if you have this H0 added to it, H0 constraint or the prior, then if you with your CMB...
Only about the late time local, not Planck.
but you are fitting Planck and H0 together, right?
Okay, without Planck it will all be 74.
Yeah, because there is nothing to...
POA data without Planck.
Yeah, it should basically Planck gives you a very early universe anchor. That is why it is stopping H0 to go very high. So if you add Planck, then the chi-square improvement is of the order of 20. Planck plus H0 with respect to the lambda CDM. If you add dark energy survey, DES or KIDS data, kilo degrees survey, then it can be as much as 30, 32 delta chi-square. So if you have 3 or 4 parameters or 5 parameters, it can fit the data perfectly. Now the thing is that the race is who can do it with the less number of free parameters. So there is a work by some people who shows that lambda SCDM, it is like a switching mechanism. They do not show how it can be done. They are saying that rho lambda was positive till some point and then rho lambda becomes negative. So Anjan...
I think D Valentino.
No, it was, okay, I will give you the name later. I just have to, okay. Now,
Switches from minus to plus.
yeah, around redshift 2 or 2.3 to be precise. And that gives them something like say 18 or 19 improvement in chi-square if you have Planck and H0. Since they have just one parameter, Bayesian evidence becomes 15 or 16. Now, if it becomes 3 or 4 parameters like early dark energy model and things like that, it basically comes down. And Professor Sengupta was asking regarding whether there are physical mechanism that are there in order to find some early dark energy or this kind of dark energy. Late time dark energy I am not much aware of, but one of the models that has been very successful, but now people are now started criticizing because it is not fitting the other data well as well. That is the early dark energy model by Vivian Poulin et al. And Mark Kamienkowski. So they say that around redshift 3000 or something like that, matter radiation equality, there was a dark energy component that was going up. They are saying it can be done by oscillating scalar field, oscillating scalar field, that was one of the explanation. Then there was new early dark energy by Niederman and some other groups. They are saying that probably decay of a false vacuum, like Coleman-Delucia bubble or something like that, that can give rise to this kind of thing. But they just stop it up to that, then they treat it phenomenologically. The thing is that people are not going too much into this because as soon as a new data comes in, it says that, okay, the spectral tilt, now Atacama Cosmology Telescope, it was able to fit well, but now SPT data is there, South Pole Telescope. It is saying, no, my NS is 0.96. Now early dark energy is not favored. So people are not investing more time on finding the actual or underlying physical processes that give rise to this kind of things. But till 2022, there has been a considerable effort in finding early dark energy thing. Yeah, actually they are working on this string guys as well, so that they can find certain things. Actually, I think after early dark energy, there has been several hundreds of papers written on that, trying to get a high energy perspective for that model.
Thank you very much, Dheeraj. Is there any other question or comment? Okay, but anyway, she can go up again, I'm sure. if there is any question or comment. Otherwise, let us thank the speaker and all the questioners for a very interesting session. We now break for coffee.